All right, here we go. Welcome to physics video 3.4 about friction. We've already talked briefly about friction, and basically what I've told you so far is what it says here on the screen, which is that friction is a force that sort of tries to prevent two objects from sliding across each other. It's always going to act in the opposite direction that the object is moving, or in the opposite direction that you're attempting to move it in. Okay? This chunk of notes today is basically going to be one big example here. Is going to pertain to a big safe. I forgot to change this. Not a freezer. Okay, so what I would like you to do is imagine a large safe sitting at rest at the center of a warehouse. All right, Roy is going to push the safe around on the floor, but because the floor of a warehouse is significantly rougher, less smooth than a bowling alley, like we used a couple of videos ago, we got to consider friction. All right, so here's what you got to know about the force of friction. First of all, it's lazy. Friction is going to always exert as little force as possible to prevent the two objects from sliding across each other. Okay? So if friction is able to prevent the objects from sliding, it's going to do that by exerting as little force as possible. Okay? Keep in mind that it's not always able to keep it at rest, prevent the objects from sliding. But if it is, it'll do it by exerting as little force as possible. Okay? Now, anytime two objects rub together, there is what I sort of call the maximum amount of force that friction can exert. All right. How much force that is depends on what the two surfaces are. If they're like rough surfaces, like rubber on cement would mean more force. A hockey puck on an ice rink is going to be less force, right? So it depends on what the two surfaces are, and it also depends on how tightly they're being pressed together. Which is why heavy objects seem harder to move, because since they're heavier, there's sort of more force pressing it down to the surface it's sitting on, so there's more friction because it weighs more. Okay? So finally, this last bullet is really kind of the important one, and it's going to sort of help us. It's sort of the philosophy that we're going to use to solve any problem dealing with friction. All right, so here's the deal. If friction can prevent objects from sliding, it'll do so by exerting as little force as possible. But if the two objects are already sliding, friction is going to exert the maximum force, okay? Because once the objects are sliding, friction doesn't want it to, and so it's going to exert the maximum force to prevent the objects from sliding anymore. All right, so on to the big example. So here we go. We've got a 75 kilogram safe, which happens to be full of ice cream, sitting at the center of a warehouse. Friction between the safe and the floor, in this example, can exert a force of up to 450 newtons. Again, that's specific to just this example. Our force of friction maximum is 450 newtons. So that's the most force friction can exert. So the safe is going to get pushed around on the floor. I want you to tell me what the safe is doing at the end of each time interval. Okay? Be detailed and give as much information as possible. Here we go. So we need to start by drawing the safe. So here's the safe. We said the mass of it was, I've already forgotten, 75 kilograms. So remember to write your mass inside the box. And then you've got the force of Roy, right? So here's our force of Roy. It's 300 newtons. He's pushing it for a time of 2 seconds. Now remember, there's friction here. Friction doesn't want the box to move. So the question is, can friction prevent the motion? Can friction keep the velocity constant, right? Because right now our velocity is 0. So the question is, can friction keep the velocity constant? Well, to do that, it would need to make the net force 0, right? So can it make the net force 0? Well, the most force friction can exert is 450 newtons. So friction's going to push this way, but it doesn't need to exert all 450 newtons. It only needs to exert 300 newtons to prevent the motion. So imagine pushing on something but not with enough force to get it moving. That's what's happening here. All right? Roy's pushing with 300 newtons. It's not enough force to get it moving. Friction pushes back with 300 newtons. The net force is 0, and the velocity stays constant. Okay? So that's it. It's going to stay at rest. Nothing happens there. All right? Now, let's suppose he increases his force up to 450 newtons. All right? Well, now, here's our box, 75 kilograms. Here's Roy pushing it. Once again, remember, friction's going to try to prevent it from moving. And it's got 450 newtons that it can use to do that. So again, you ask the same question. Right now the box is at rest. Can friction exert enough force to make the net force 0? And the answer is yes, friction is going to exert, in this case, negative 450 newtons, right? Keeps it at rest. So once again, it still doesn't move, okay, because Roy hasn't exerted enough force to get it moving, all right? In order for him to get it moving, you're probably realizing now, he needs to exert more than 450 newtons. So in the next example, now he's pushing with 600 newtons, which is way more than 450. So let's draw it now. What's going to happen? Here's our box. It's 75 kilograms. Here's our force of Roy, 600 newtons. Okay? Remember, our velocity begins at 0, and friction wants to keep it at rest. Friction wants to keep the net force 0. All right? So it's going to push back, trying to keep it at rest. Here's our force of friction. So before, I just made it so that the force of Roy and the force of friction were equal. But that can't happen this time. Friction can't exert 600 newtons. So it looks like friction's not going to be able to make this net force be 0. So what's going to happen is it's going to do everything in its power to prevent it from moving. It exerts the maximum force, but that doesn't keep it from moving, right? So in this case, what's going to happen is we're actually going to have a net force. Now the box is starting to move. Roy has pushed with enough force to get the box moving. So our net force is going to be the 600 newtons from Roy plus 450 newtons from friction. So our net force is 150 newtons, which means that we're going to actually have an acceleration, aren't we? So our acceleration is going to be net force over mass, 150 newtons divided by our mass, which is 75 kilograms. You're going to get an acceleration of 2 meters a second squared, right? It's going to literally accelerate. So now our velocity is going to change, right? So let's see what we know. We know our initial velocity was 0. Our acceleration, we just found it. It's 2 meters a second squared because Roy's pushing with enough force to get it moving. We don't know the final velocity, but we know that he's pushing it for a time of 6 seconds, according to the problem, right? So what's going to happen now is the box is going to speed up, right? So let's find our final velocity using this guy. The velocity begins at 0, and then it goes up by 2 meters a second every second for 6 seconds. So the box is going to increase until it gets to 12 meters a second. So there's your final velocity. Okay? So what I want you to understand here is, in the first couple examples, friction was able to keep the box at rest by exerting, smaller numbers, right? If this force here had been 150 newtons, this would have been 150 newtons. 200, 200, 300, 300, 400, 400. 500, friction can't exert it. 600, friction can't exert it. And so that's what we run into here in this last example. Friction can't exert 600 newtons, so it exerts the maximum force that it can. There's still a net force, so you get this acceleration that we found here. All right? So now what if he pushes with 300 newtons? This is where people tend to get a little bit confused. So follow along here. We got 75 kilograms. Based on our last problem, the safe is already moving at 12 meters a second, right? Remember, friction doesn't want it to move, right? So here's what Roy's doing. Roy's pushing this way with 300 newtons. Now, remember, the box is moving. Friction doesn't want it to move. So friction's going to push back with the maximum force. Anytime the box is moving, friction exerts the maximum force. That's what you need to get here. Okay? So once again, now we find our net force. It's going to end up being negative 150 newtons, right? It's 300 minus 450. Find the acceleration. So now our acceleration is going to be negative 2 meters a second squared, right? So the velocity is going to decrease by 2. So let's see, we know our acceleration is negative 2 meters a second squared. Velocity is going to decrease by 2 every second for 2 seconds. So find your final velocity using this guy. So the box is going to slow down to, in this case, 8 meters a second if you plug those numbers in. Okay, I was hoping to keep this under 10 minutes. Okay, but so the point here is Roy's pushing it forwards with 300 newtons, but it's not enough force to make it speed up. It's not even enough force to keep the velocity constant. So now friction is winning. It's going to slow down. And if Roy kept pushing with 300 newtons, it would keep slowing down and eventually stop. Okay? So now what happens if he pushes with 450 newtons? Well, here's our box, 75 kilograms. based on the last example, the velocity is 8 meters a second, right? And now, Roy's pushing with 450 newtons. Remember, friction doesn't want it to move. It's sliding, so friction's going to exert the maximum force of 450 newtons. So now what's our net force? It's going to be 0, right? So now the velocity is constant. Okay, he had to push with more than 450 newtons back in, what was it, part C, to get it moving. But now that it's moving, just 450 newtons will keep it moving. Okay? All right, finally, if he pushes with 600 newtons, it'll accelerate again. Okay, I'm going to skip this one because I don't think that this is instructive at all. All right, you would just end up with a net force of 150 newtons and it would accelerate more. Okay, so we're going to pretend that part's not there. So right now our box is moving at 8 meters a second. So we're going to jump ahead to the next part. Roy completely lets go of the safe. And this is the last one. Okay, so here's our box, 75 kilograms. It's moving along at, we just said, 8 meters a second. Remember, friction doesn't want it to move. So friction's going to try to stop it with a force of negative 450 newtons. That's the max, right? And since Roy completely lets go of the safe, that's it. There is no force of Roy. All right? So our last step then is identify our net force. In this case, it's negative 450 newtons. Let's find our acceleration. It's net force over mass. So negative 450 newtons divided by 75 kilograms gives you negative 6 meters per second squared. So it's going to slow down and eventually stop, right? So let's find the time to stop. Here's what we know. We know our time. Eventually it's going to stop, right, if he doesn't touch it again because he's completely letting go of it. We just found our acceleration, negative 6 meters a second squared. So we can find our time. So the velocity is going to go to 0 from 8 at a rate of 6 meters a second squared. So that's going to give you 1.3 seconds, and it will stop. All right. I believe that's it. That's friction. Oh, I've lied to you guys. You know what? Do this, and we're going to start the notes with it tomorrow. See if you can try this problem. There you go. Done.